recording this. So if we need to graph this, what's something we could tell about this right away?
It looks like x to the fourth.
Okay. It's
And
like
it crosses at 0, 8.
x to the fourth crosses at 0, 8. Okay. Anything else?
It can have a possible of 4 zeros.
It could possibly cross the x-axis 4 times. It could have 3 turning points. Anything else? Okay, now you took a quiz yesterday where most people did pretty well on those, got them figured out and everything. What's the difference between graphing the ones you did yesterday? Because some of those were x to the 6th. They were already factored. This isn't factored. Any ideas?
You can factor it.
Yeah, let's factor it. And we're going to do the what? I heard it over here. Do the P and Q stuff. So let's put P equals 8 and Q equals 1. This is good news because we can say, well, 1, 2, 4, and 8. Put commas here, put pluses and minuses in front of each one of them. So I have, if there are any nice zeros, this happens to cross at really nice places. Okay?
The only problem that does
Okay. Does a 1 work?
no.
Okay, if you plug in a 1, you get 1 minus 1, negative 6 plus 4, and then plus 8. So negative 1, or 1 doesn't work. Does negative 1 work?
Yes. I don't know.
Okay, well, let's check and see. So I'm going to change colors. If I plug in a negative 1, this is a 1, right? This would be a plus 1. This would be a minus 6. This would be a plus, minus 4, thank you. Minus 4, and this would be a plus 8. So if I add all those together, I get 0. So that means we know for a fact that this is a 0, but that doesn't really do us any good because we want to factor the whole thing, right? So we're going to do synthetic division. So I'm going to put negative 1 in the box. Now we know what the answer is going to be. We're just going to go through and take a good look at this. Make sure we write everything down nice and neat. We know what's going to go in the box. We know there better work out to be a 0 there. So bring down, multiply, add, multiply, add, multiply, add, multiply, add. Worked out. Now, again, what that means about this is it's a 0. What is this stuff right here? That's the depressed polynomial. So what I'm going to do is I'm going to bring this down here because I like keeping track of what the factors are. The factor that corresponds to this is x plus 1. And then the quotient, the thing that we got when we divided, that depressed polynomial is x to the third minus 2x squared minus 4x plus 8. Any questions?
Yeah, we can factor it.
Thank you very much. What's nice about this depressed polynomial, they're lower degree, they're usually easier to work with. And if we get lucky, like we did on this one right here, what did you say? Whoops. What did you say, Tyler? No, I'm serious. What did you say here?
Oh.
You can factor it. Look at this. I've got an x cubed and then a minus 2x squared. Look at the pattern here. That's a 1. That's a negative 2. It's the opposite sign and twice as big. That's a negative 4. That's a positive 8. It's the opposite sign and twice as big. So I'm going to take out an x squared. I'm left with an x minus 2. What am I going to take out of here? Okay, take out the leading sign and the number 4. So this is going to be x minus 2. So I get x minus 2, x squared minus 4. And I don't want to forget that x plus 1 here.
Minus 4? Yeah, that
No, this is right to here, isn't it?
yeah, but
Okay, hold on. To here, is this right?
yes.
Am I done?
No.
Thank you very much. What can I do now? Now I can factor this. This is a difference of squares. So see how that depressed polynomial just gets easier and easier? So here's what I've got. I've gone from the original version to this one. Y equals, now let's think about this for just a second as we write this down. X plus 1. I've got 2x plus, or x minus 2s. What's the best way to write that? X minus 2 quantity squared, and this one is x plus 2. Now, I'm not going to finish this one, but if you know how to do this, then you're in really good shape for 5.6. Because in 5.6, you're going to be asked to find the zeros, factor it, maybe do some graphing and stuff like that. Okay, if you can do this, you're in good shape for the test questions. Okay? there any questions? Okay, you can finish it from there, right? Okay, there was one thing I cautioned you about. This is -1, this is 2, and this is -2. When you do the touch and cross thing, make sure you go find, like when you get to -2, don't look at this one and say, oh, it crosses because it's odd. Make sure you keep those straight, okay? You with me? Okay, all right. Go ahead and put that away. We will correct that on Monday. You should, I'm hoping you only have a couple problems left. That's a legitimate question there. Okay, but again, is this very hard? Could you think your way through this, even without me showing you? Okay, all right. Well, that's what you want to think of, because listen up. You're not going to be asked any questions for the most part. Occasionally there'll be one way toward the end or something like that, or maybe you don't have all the tools you need, or you'd have to think really, really hard. But on this one, we're kind of, if you want to call all of this one step away from what the quiz was yesterday. Yeah.
So I graphed it and it doesn't graph right. Because it crosses at -1.
Mm-hmm.
And then it crosses.
It'll work out right. I promise. Okay? All right, so I'm going to get rid of that. And let's take a look at 5.6. So this is the next section. We've got a few starter questions here. So just like last time, we talked about what the word rational means, and then we talked about what integers are. By the way, you certainly don't want to forget those. You need to know what a rational number is, how to describe it. And you need to know what an integer is, how to describe it. What's an integer again?
That's every number but 0. I mean,
No.
including 0.
Every
So
whole number.
positives and negatives including 0.
Positive and negative whole numbers, including zeros. That's what integers are. Rational numbers?
Fraction.
Numbers that can be written as fractions. Any number that can be written as a fraction, as long as you've got an integer on the top and an integer on the bottom. Okay? Got it? Okay, so what is a real number? Integers are real numbers. They're part of the real numbers. Rationals also. Okay, I like that one. Okay? Any number that you're aware of, okay? Any number without an I.
Can't it just be any real number? Oh,
That's there we go. Thank you very much. Okay. What is an imaginary number?
Something with an I.
Okay. Any number with, now we're kind of speaking informally here, but that's a decent description of what it is. What's a complex number?
all of it.
Okay, what you get when you put all of those together. Any number that you can think of right now. In fact, I've got a couple degrees in math. I can't think of a number that's not a complex number. Okay? So if I say the number 7, 7 is a complex number. If I were to write it with its I part, its imaginary part, it would be 0i. Now, if I write the number -3i, that's a complex number because the real part would be 0. Okay, it's any number of the form, anybody know? A plus bi. A is the real part, b is the imaginary part. Now, if I write this number right here, let's say I write 2 minus 3i. If I say what's the real part, you would say 2. If I say what's the imaginary part, you say -3. Don't include the I. Okay, that's a little bit redundant. So the real part is 2, the imaginary part is -3. You with me there? Okay, now if I write something like this, let's say we write a really ugly number, radical 17.1. Is that a complex number? Yes, it is. This is the real part, the imaginary part would be 0i. Okay? Any number that you can think of is a complex number. Okay? We break them into the real part, imaginary. Put those two together, you get the complex numbers. Okay? All right.
How would you define infinity?
More of a concept than a number. Okay? The idea that something gets larger and larger and larger and never stops getting larger and larger and larger.
So infinity is an irrational number, correct?
Infinity's what?
An irrational number?
No, you can't classify that because it's not a number, it's an idea.
Oh.
It's a concept. Okay? Okay, so we've got a couple theorems here. we'll be done with the theorems fairly quickly. Now the theorems are a little bit wordy. They look kind of ugly. We're going to be done with those pretty quickly. And then the rest of this is just applying these ideas. And when we get done with each theorem, we're going to kind of put it in normal speak. Okay? Instead of a bunch of math terms, we're just going to say, well, in other words, this is what this means. Okay? So in the last couple sections, we've been dealing with real zeros. We've been graphing these, finding solutions to equations and stuff like that, finding x-intercepts. But we've been dealing with all real numbers. Okay? So if it had an imaginary solution, one with an I in it, we weren't really worried about that because it didn't cross the x-axis in that place. It wasn't a real number. Okay? Now in this section, we're interested in finding all of the answers. We don't care whether they're positive or negative. We don't care whether they're rational or irrational. We don't care if they're real or imaginary. We want every single one of the answers. Okay? Yeah.
How do you graph an imaginary number though?
Well, if you think about it, when you did parabolas and you found parabolas that had imaginary zeros, what did that mean about the parabola? It never touched the x-axis. So you can't graph it on the real plane. Okay? It doesn't produce any x-intercepts, but there's still solutions to the equation. Think about that for a while. You've solved quadratics.
Give me a headache.
You've solved
No,
quad.
but like, would you just graph it and just forget the zeros, I guess?
Yeah. As far as where they are on the xy plane, yeah, you wouldn't worry about them
Oh, okay.
because it's a real plane. It's not an imaginary plane. Okay. All right. So we're going to go over something called the fundamental theorem of algebra. This is how important polynomials are. There's a theorem in algebra, and it is the fundamental theorem of algebra. Okay, it's like the basis for a lot of the stuff that's done in algebra. And it says every complex polynomial function of degree n greater than or equal to 1 has at least one complex zero. Okay, so all this means is if you're dealing with a polynomial that has complex coefficients, usually we deal with ones with real coefficients, not imaginary coefficients, then we're guaranteed that there's at least one complex zero. So all this means is we're guaranteed at least one zero. If it's at least degree 1, we're guaranteed that we're going to find at least one complex zero. Okay, the next theorem. No fancy name for this. I'm going to read it and then we're going to put it in just kind of layman's terms here. It says every complex polynomial of degree greater than 1 can be factored into linear factors. Okay, not necessarily distinct. In other words, they'd repeat. Remember on the one that we just did a minute ago? We had a factor of x minus 2 and another factor of x minus 2. That's okay. It's just a repeating linear factor. Okay? So what we can do is we can take that polynomial and we can break it up into a bunch of linear factors. And it says all of these, R1, R2, all of those, that stand R's for root. Okay? Those are all complex numbers. Okay, now basically what that means is we can factor, okay? We're guaranteed that every polynomial can be factored using complex numbers. So we don't have to worry about getting stuck. We know for a fact we're going to be able to factor everything down into these nice little linear factors. Okay? Next one, and this is kind of a cool one. We're going to use this all the time. It's a really nice idea. It says if we've got a polynomial where the coefficients are real numbers, and a plus bi is a zero or a root, then its complex conjugate, what's the conjugate of a plus bi? A minus bi, that's also got to be a zero. So imaginary zeros come in conjugate pairs. Imaginary zeros come in conjugate pairs. I should have had a blank for you to fill in there. All right? So what that means is, if I know that 2 plus 3i is a zero, a root, a solution, an x-intercept, whatever you want to call it, okay? That couldn't be an x-intercept, though, because it's an imaginary number, right? Okay? So if 2 plus 3i is a zero, what else is a zero? 2 minus 3i. Okay? It's that simple. It's really cool. So if you know one of the imaginary zeros, you've got another one. Automatically. They always come in pairs. They always come in conjugate pairs.
Forever and ever?
Yes, if you want to say forever and ever, that would be fine. Okay? All right, next one. This is called a corollary. A corollary is like a related theorem. Okay, this one says a polynomial of odd degree with real coefficients has at least one real zero. A polynomial of odd degree has at least one real zero. Now, I want you to think about that for a second, because we already talked about this. If you have an odd polynomial, we argued the other day as to why it would have to have at least one real zero. What was the reason? Yeah.
Because it starts underneath the x-axis and goes up.
Starts down here and goes up here, and that was the intermediate value theorem. Okay? Can't go from down here to up here in one piece and not cross through zero. Okay? And yet, why didn't we introduce that, and why did we call this a corollary to this one right here? If it's an odd degree, how many zeros will it have? Okay, it will have at least one. Let's say I've got a degree 5 polynomial. It can have up to 5. Okay. Now, complex-wise, it's going to have 5. If we're looking for all of them, it's going to have 5. Why are we guaranteed at least one of them will be real? It relates to this theorem right here. They come in pairs. So if I'm looking for 5, let's say one of them is an imaginary one. That means I've automatically got 2 of them. Let's say I find another one that's imaginary. I've got another one that's 2 so that's 2 of them. Okay? I've only got one left. Is there any way it could be imaginary? It couldn't be. It would have to be real, because if it was an imaginary one, we'd have to have another one which would give us a total of 6. See the logic there? See how these are related? No?
Yeah.
Okay. Okay, let's say I've got one imaginary one. If I've got one imaginary one, I automatically have the conjugate to that. So I've got 2. Let's say I've got another imaginary one. I've got the conjugate to that. Now I've got 4. So there's only one left, because there's going to be 5 total. There's no way that one could be imaginary, because it would have to have a conjugate, and then that would give me 6. Does that make sense?
Yes.
Good? Okay, so we've got 2 arguments for why if it's an odd polynomial, odd degree polynomial, we've got to be able to find one real zero. So in other words, if it's odd degree, we're guaranteed at least one real zero. That polynomial will have at least one x-intercept. It's got to cross the x-axis in one place. Okay, and then the last theorem that we're going to talk about, and now we've got all the tools that we need to deal with these polynomials. Every polynomial with real coefficients can be uniquely factored over the real numbers into a product of linear coefficients, and we mentioned this the other day, irreducible quadratics. Okay? Now here's what this means. If we're using only real numbers, so we're not worried about the complex ones, we're guaranteed that we can factor it into linear factors and or irreducible. Make space for that. Irreducible quadratics. Now, there's no problem with an irreducible quadratic. Let me show you some examples. If I did all my work and I ended up with this right here, this was the last thing that I was trying to factor, what could I do to find the answer to that one? Set it equal to 0, move it over to the other side, take the square root of -9. There would be the imaginary answers. Let's say I had this one right here. That was my irreducible quadratic. What can you always use to solve a quadratic? You can use the quadratic formula and it would give you the other answers. Okay? So, if you put all these together, we're guaranteed that we're going to be able to take any polynomial that we're given and break it up into a bunch of factors. And if I get to a point where I can't do it with real numbers, or it's an irreducible quadratic, I can throw it into the quadratic formula, figure out the answers that way. Okay? All right, so let's take a look at a couple of these examples. Okay, so this one says, and I want you to notice the difference in the instructions. On example 1, it says, find all the zeros of the function. Now, if you think about 5.5, it said only real ones. Okay? Now, if it's degree 3, it could have up to 3 real ones, but we don't get any guarantee that all 3 of them are real. Okay? Maybe one's real and the other 2 are imaginary. Remember, they come in pairs, right? See the logic there? Yeah.
So if we did this problem, we found 2 real ones that automatically have to make a third one.
Exactly. Hear the logic there? If you go through and you find one real one, then you find another one, there's no way the other one's imaginary. Okay? You've got to have all 3 real ones. Okay? All right. Any questions? Okay. So let's go through and do this, and it says find all the real zeros and then factor the polynomial. So this isn't any different than what we did just a second ago. When we were factoring that other one, we're going to use the same technique. So what am I going to start with, Trevor? P's and Q's. So I'm going to do P equals 6, and I'm going to do Q equals 1. We like it when Q is 1. So that means my list of possible nice zeros looks like this. 1, 2, 3, and 6 are factors of 6. The only factors of 1 are 1. So if you do 1 over 1, 2 over 1, 3 over 1, 6 over 1, there's my list. Okay, these are the possible rational zeros. I need to make sure I find them all. Whether they're real or imaginary doesn't make any difference. And we're guaranteed we're going to be able to do that using this theorem here. Now, how many am I looking for? I'm looking for 3. Okay? All right, so let's check and see. Does 1 work? It's cool when 1 works, right? Because this is a 1, that's a minus 2, that's a minus 5, and that's a 6.
So it does work.
It does. Okay? That's a negative 7, that's a positive 7, so 1 does work. Again, that's just a quick way to check that. That's not a very helpful way to finish the problem, but at least we know when we plug in a 1 and do synthetic division to produce that depressed polynomial, we know what our answer is going to be. We know it's going to go in evenly. We just make sure we need to do this carefully.
That's helpful because then we know that we have at least one.
So this is going to be a 1. That's a negative 1. Multiply here. That's a negative 1. That's a negative 6. That's a negative 6. That's a 0. So just like we suspected. That means this is a 0. And that means the factor that it corresponds to would be x minus 1. And then I get this.
And it's pretty. And then
Why is this pretty, Sarah? Yeah, it's a quadratic, so we like quadratics because we have so many tools, and this happens to be an easy quadratic to deal with because we can factor it. So we're going to go ahead and factor that. We're looking for numbers that multiply to be negative 6 that combine to be negative 1. So that's going to be negative 3 and positive 2. Okay there? And that's x minus 1. Now, I've got the polynomial factored, so I'm going to write that up here. So this is going to be x minus 1, x minus 3, x plus 2. So that's part of the work. And then the other work is just writing down the zeros. All we have to do is write down the zeros. So that's going to be a 1, a 3, and a negative 2. And I'm finished with the problem.
That's not going to be that easy.
You're right, so we started it off easy. Okay, got it? Now, you're right. If 1 hadn't worked, we would have had to check negative 1. And what if negative 1 hadn't worked?
Check 2.
We probably would have gone through the list and checked 2, and then negative 2, and then 4, or 3, and then negative 3, and so forth. And maybe it would have taken till we got to negative 3 before we got one that worked, but then at least we'd have a depressed polynomial that's a quadratic, and we know we could finish it from there. Does that make sense? Okay, now, what you need to think about is, when you're doing these problems, McKay, there we go. When we're doing these problems, I realize, like I've mentioned before, nobody is going to stop you at the grocery store and check to see that you can factor a 5-term polynomial. Okay? They're not going to care that complex zeros or imaginary zeros come in conjugate pairs. Okay? But if you can think your way through complicated problems like this, then you're the type of person that they'll probably hire at some big engineering firm to figure stuff out. They might pay you a lot of money. You might get accepted to med school. You might be a better attorney or even a better parent if you're able to figure out complex problems. Because believe me, teenagers, oh, that's problems. Okay, got to figure those out.
Adults are pretty complex too.
That's right, they are.
Oh, you're great.
Okay, which means you'll just be better all around. Is that what I'm hearing?
Yes.
Okay, so let's take a look at the next one. Okay, the next one says find all the zeros, then factor the polynomial and graph it. So let's find all of them. Now, we'll look through here. We know we're looking for how many? We're looking for 3. Now, they might all be real. They might all be rational. They might all be nice. Maybe there are some ugly ones. Okay? But if we're going to find them, again, we're going to do the P and Q stuff first. So this is a 3 and this is a 2. Now, the minute I have a Q that's not 1, I get an uglier list to check. So I get a 1 and a 3. I get a 1/2 and a 3/2, right? Does anybody need to see how we got those? It's an uglier list though, isn't it? Okay? Okay, John is over there smiling. Tell us, John.
1x minus 1 is a factor.
John is nearly giddy because if you check right here, 1 works, doesn't it? Because that would be a 2 minus a 1. That'd be 1 plus 2. That'd be 3 minus 3. So 1's going to work. So luckily this one works. Let's go through and define the depressed polynomial. So we got a 2, bring down, multiply, add, multiply, add, multiply. There we go. So this means this is a 0, and it corresponds to a factor of x minus 1, and we've got 2x squared plus x plus 3. Now, we'll take a look at that for just a second. Did I make any mistakes here? Didn't make any mistakes. I don't think so. Okay. Okay. Those would multiply to be 6. Are there any numbers that multiply to be 6 that combine to be 1? So forget guess and check. You could guess and check all you want, and it's not going to factor. Any questions?
Explain the last half again, because I thought it did factor.
Okay, you could do guess and check. You could put these down and do a 2x here and an x there and put 3 and 1 and all sorts of orders. But you can check by taking the number in front, that coefficient here, the constant at the end, multiply them together, you get 6. And then just say, can I find anything that multiplies to be 6 that combines to be 1? If it were negative 6, we could make a positive 1. But if you do 2 and 3, those add up to 5. And if you do negative 2 and negative 3, they add up to negative 5. Okay?
I'm on the same track as you now.
Good. Got it? So, what do we know about this? They might be imaginary. They might be imaginary. Okay? But in order to solve this, in order to find the answers that come from here, what would I have to use if it doesn't factor? I have to use the quadratic formula. So here's what we're going to do. I'm going to take a look at this. I'm going to underline this in blue, and then I'm going to do the work for this in blue. So this is going to be x equals negative 1 plus or minus. This is going to be 1 squared, so that's 1, minus 4 times a times c. And again, we mentioned this before. Please don't mess up that work right there. This is where people make mistakes. I'm going to write 1. Am I adding to 1 or subtracting from 1? I'm subtracting from 1. And I'm subtracting, that's going to be 8 times 3. That's going to be minus 24. Is that right? So what I get here is x equals, this is going to be negative 1 plus or minus radical negative 23 over 4. Now in 1010 you practiced writing them that way, and sometimes you left it that way. And then other times you broke it into a couple different pieces. So I'm going to break it into a couple different pieces. One of them is going to be negative 1 plus radical negative. Well, wait a minute. I don't want to leave it like that, do I? We want to take an I out. So this is going to be, boy, that sounds funny. Okay? So we take that out. We've got this over 4. And the other one is negative 1 minus I radical 23 over 4. Now, it may not seem like we're done, but as far as finding the zeros, we're finished, and I want to show you something else. I'm going to go through here and I'm going to list the zeros. The zeros are 1. This one is, now watch carefully, this one is negative 1/4 plus I radical 23 over 4. And look at this one. Negative 1/4 minus I radical 23 over 4. Take a good look at these two.
They're conjugate.
They are, aren't they? So if I wrote this one down as negative 1/4 plus I radical 23 over 4, immediately I know imaginary zeros always come in complex conjugate pairs. Okay? So it's got to be the exact same expression. It's just got a negative there instead of a positive. Any questions there? Okay, one more thing before we graph. It says factor. This is x minus 1. Okay, now watch carefully. This is going to be x minus all of this stuff. What's it going to do to the negative 1/4? It's going to make it positive. What's it going to do to the positive I radical 23 over 4? Make it negative. And then this one is going to be x minus this stuff, so that's going to be plus 1/4. And then this is going to be plus I radical 23 over 4. Okay, so here are the zeros, there are the factors. Are there any questions? Okay, now earlier Marissa said, well, what if you get imaginary zeros? How do you graph those? Okay, is this a point on the x-axis? Nope. Is that? Nope, so we don't worry about it. So of these three zeros, what's the only one that we graph on the x-axis? Just the one, okay? So we're going to put a 1 right here, crosses at 1. Okay, now what does this look like? 2x to the third. What's the multiplicity of this 0? 1. So it crosses. Now, if I'm going to do this right, it's going to start down here and it's going to end up here. I should maybe label one other point. So it's going to do something like this. What is this point right here? Okay, so this is 0, -3, and this is 1, 0. Now, are there any questions on that? Because we're going to take just a slightly closer look at this. Sure? Okay. Without knowing, now remember, this can have up to 2 turning points, right? How did I draw mine? Doesn't have any turning points. Okay, is that okay? Mm-hmm. It says up to 2 turning points. It doesn't say it has to have 2 turning points. So, is there any way for me to know whether it did this? Because that would work too, wouldn't it? This would be an acceptable graph. Make it cross at -3 and +1. Or this, let's see. That would be a little bit of a stretch, but I mean, it could have been either one of those two. For the purposes of this class and for the tools that we have so far, is there much difference for us between these? No, there's not. Now, if you're in a calculus class, you can figure out whether or not it actually has turning points. Okay, I suspect that this does, but we're not required to find that. That's a decent sketch of the graph. That's the basic behavior we're interested in from a pre-calculus perspective. Okay? Good? Okay. All right, that's pretty much the ideas. Let's take a look at example number 3. A polynomial of degree 5 with real coefficients has zeros of 1, 5i, and 1 plus I. Find the remaining zeros. So this is where that thinking comes in, that logic. If it's degree 5 and one of them is 1, okay, I'll take that. I can't do anything else with that. If another one of them is 5i, hey, wait a minute. They always come in conjugate pairs. So if 5i is a 0, what else is? -5i. Then they said 1 plus I is a 0. And again, we say, hey, wait a minute. I know they always come in conjugate pairs. So 1 minus I is, and how many do I have?
5.
I've got 5 altogether. Do I need to worry about finding any more? Nope, because there can't be more than the degree. Yes. Yes. Mm-hmm. It is, isn't it?
Show our work, though, 'cause
No, that's it. That's it. No, your work's up in your head. Okay? Okay. Any questions? Okay. So the reason you don't have to show any work is really, I mean, this is complicated enough. There's no work to show. You've got to have it in your head. Otherwise, there's no way you'd produce the right answer. Okay? All right, so let's take a look at example 4. It says a polynomial of degree 4, or excuse me, find a polynomial of degree 4 with real coefficients that has zeros of 1 with a multiplicity of 2 and -4 plus I. So if this has a multiplicity of 1, so first of all, if 1 is a 0, what's the factor that it comes from? X minus 1. And if it has a multiplicity of 2, square it. Now, if I know negative 4 plus I is a 0, what else is a 0? Negative 4 minus I. So if I write down the factor that corresponds to this, this is going to be x minus negative 4 plus I. Now, I'm going to rewrite this. I'm going to erase this in just a second. If I subtract a negative, what do I get? A positive. And if I subtract a positive, I get a negative. So I'm going to rewrite this as, this would be plus 4 minus I. And the other one would be minus a minus 4 plus 4 minus a minus I plus I. Now, take a good look at this. These should still look kind of like conjugates. X plus 4 minus I and x plus 4 plus I. Now, it says find the polynomial. This isn't a polynomial. It's the factored polynomial. So how would we find the original polynomial? Okay, we do have to multiply this out, but I want you to watch. This one should not be hard, and you should immediately know what the answer is. When we square a binomial, we get a perfect square trinomial, and that is x squared minus 2x plus 1. That's what we get from this one. You with me? Okay. If you want to multiply these out and do x times each one of these, 4 times each one of these, and negative I times each one of those, that's 3 terms in the first one, times 3 terms in the second one. You're going to get 9 terms altogether, and then you're just going to collect the like terms. You could do that, right?
Yeah, but
Yeah.
they're conjugates, so some things are going to cancel out.
Yes, you're right. You're going to have 9 terms, and a bunch of things are going to cancel out. Do you want me to show you a shortcut for that?
Yes, please.
Okay? So these are conjugates. Conjugates is a fancy word for difference of squares. So if I look through here, I should be able to find where the difference of squares are. That's this minus that, and the same thing plus that. Not quite. Not quite. If you watch, what we'd have to do is we're going to take this and multiply it by that. And we're going to take this and multiply it by that. It's going to end up being a difference of squares, so it's going to be a difference of x plus 4 squared minus I squared. Hold on. It's not that easy. Okay, now if you don't see that, that's fine. Multiply the 3 terms times the other 3 terms, get the 9 terms. A bunch of them are going to cancel out. In fact, all but 3 of them are going to cancel out. Okay, collect those terms together and you're all set to go. So here's what we get. This is x squared plus 16x plus, 8x plus 16. This is negative I squared. What does negative I squared count as? This counts as positive 1. So this is x squared minus 2x plus 1 times x squared plus 8x plus 17. Now, is there any way to get out of multiplying these big ugly polynomials together? No, you need to multiply those together, and that will be your 4th degree polynomial. Okay, so that's how you'd finish it off. Do you have a bunch of those? No, I think you have 1 or 2 of them. Okay. Any questions? Okay, you can finish this on your own. I'm not going to finish it now. It's just polynomial multiplication. You probably learned how to do that in 7th or 8th grade. Questions? Okay, last 2. Let's take a look at number 27. Okay, now again, this is where you got to use your head. This one says, given the 0, find the remaining zeros. And then write the polynomial in factored form. Now, how many zeros on number 27 are we looking for? We're looking for 4, right? Because it's a degree 4 polynomial. How many zeros? Hold on. You're getting ahead of me, Zach. Okay. How many zeros did they give us? Oh, all of you are getting ahead of me. This is irritating. Okay. How many did they write down on the paper? 1. But how many did they really give us? They gave us 2. So if they gave us this one, then we know we've got a conjugate. So we actually know that we've got 2 of these. Okay, now, if I know I've got a 0, I could go through and do synthetic division. And oddly enough, you can actually do synthetic division with imaginary numbers. It's not pretty, I actually had a student figure this out a couple of years ago on a test because they were just stressed, couldn't do it any other way, didn't know what to do with it. So they did synthetic division. It does work, but this would be the best way. I'd take these and I'd write down, hey, I've got to factor it anyway. Notice it said factor. That means one of them is x minus 3 plus 2i. And let's think in terms of conjugates. The other one would be x minus 3 minus 2i, right? Should we use that little trick again? Okay, let's multiply them together. It's going to be those two multiplied together minus those two multiplied together. So it's going to be x minus 3 quantity squared minus 2i squared.
Wouldn't it be 4i
4i
squared?
squared.
Because you times 2 together?
I'm not done.
Oh.
So this is x squared minus 6x plus 9. This is going to be minus 4i squared. What does that count as? That counts as a positive 4. So here's what I've got. X squared minus 6x plus 13. Okay, now follow the logic here. If these two are factors of this polynomial, shouldn't this be a factor of that polynomial? Okay, now look how ugly this is. This is horrible. It's a 5-term polynomial, and yet we're going to factor it. Okay, so watch. You can't get away from long division entirely, so here's what we've got to do on this problem. I've got to have an x squared minus a 6x plus a 13, and inside the box we'll go x to the 4th.
Just kidding to make me mad. Just joking right now.
You're right. This entire class is designed around you just to make you mad.
There has to be a better way, right?
Nope,
There's not?
not on this one.
Yes.
Well, let's see. No, I suppose if you wanted to go through and do, here's the other option. Somebody tell me what it is.
Never mind.
Well, yeah, you could do synthetic division, but that would take you just as much time.
Good luck with your subject.
You could do P and Q, but do you want to use?
No.
Okay.
No.
Maybe that would work, but let's take a look. What would I multiply by?
X squared is ugly.
X squared. So this is going to give me an x to the 4th. This is going to give me, let's make sure these line up. This is minus 6x to the 3rd. And then this is going to be plus 13x squared. Again, we're going to go through and change the sign. So that's a minus, that's a plus, and that's a minus. And then let's write down what we've got. No more x to the 4th. That's good news. Then I've got a minus 3x to the 3rd. Tell me if I make a mistake. And then this is going to be plus 8x squared minus, plus 21x. And then minus 130. We do okay? What do I multiply x squared by to make it a negative 3x cubed? Negative 3x. So this is going to be a negative 3x cubed. That's going to be a plus 18x squared. And that's going to be a minus 39x. Did I do okay there? We're going to go through and we're going to change signs. So that's going to be a plus, that's going to be a minus, that's going to be a plus. So I get none of those, and let's see, I've got a negative 10x squared. Put these together. This looks like good news here because that's going to be a 60. Is that right? And then this is minus 130. What do I multiply x squared by to make it a negative 10x squared? Negative 10. So I put a negative 10 up here. That's going to be negative 10x squared. That's going to be a plus 60x. And that's going to be a minus 130. And then again, I go through and change the sign. So that's a plus, that's a minus, that's a plus. And what do we notice here?
Yes, they're all gone.
They're all gone. Okay, what does that mean about this?
Factor.
Okay, let me go back down here. That means my other factor is x squared minus 3x minus 10. And what do you know about this? It's a nice one. Multiply to be negative 10 combined to be negative 3. And then all I have to do is put those in place right here. And I am finished because, whoops, that's a plus, right? Yep. Factored. It's factored, right? Zeros. There's 1. There's its conjugate pair. What are the other two zeros? 5 and negative 2 from those linear factors right there. So, okay, now put this in perspective. If I had said just a couple days ago, in fact, good grief, if I had said an hour ago, I want you to factor this 5-term polynomial, and by the way, it's got numbers like 21 and negative 130 in it. No clue. Wouldn't be able to do it. Okay, but now we can. Okay? By the way, if you had done the P and Q stuff, if we did it like we normally did, what would be the first number that we would have found that would have worked? Negative 2. So we would have checked 1, negative 1, positive 2. By the time we got to negative 2, we would have found one that worked. Got it? Okay, any questions? Okay, we're going to do the last one. Tylen's going to start because she's going to put her phone away, right? Thank you. Okay. This one says, find the complex zeros. Now that's the same as saying, find all the zeros. I don't care what kind they are. Real, imaginary, whatever. Find all of them. Okay? How many are we looking for? We got to find 4 of them. Okay? Let's do P and Q. Okay, now we're going to go a little bit over, but I'll make it up to you next week. 18 and 3. Okay, now I am going to list this. 1, 2, 3, 6, 9, and 18. 1 and 3. So if I go through and make my list is going to be 1, 2, 3, 6, 9, 18 by putting them over 1. To that, I'm going to have to add 1/3, 2/3, 3/3? Nope. 6/3? Nope. 9/3? 18/3? Nope. This is my list with the pluses and minuses on there. There's no way all of those are going to work. It's just not possible. Because we've got a list of, what does it look like? 14 of them? Yeah.
What if none of those work?
Then you're in trouble, and then you wouldn't be in this class. Then you'd be in an advanced math class at the U or at BYU or something like that. Good? Okay. All right. So what one do you want to check first?
1.
Okay, hold on. Look at 1.
Oh, that will never work.
See how they add up? We get this gigantic positive number. There's no way 1's going to work. So let's check negative 1. Okay, this would be 3. That would be negative 5. That would be 25. That would be negative 45. And this would be negative 18. Does it work? No. Now, is that enough of a time savings that we ought to check 1 and negative 1? Yeah, I think so. Okay, so check them that way. And now let's check. Stop and think for just a second. Don't.
Sorry.
It's too smart. Okay. Why would we not even bother doing synthetic division with 2? So many positive coefficients. By the time you get here, we've got some ridiculously large positive number, and all we get to do is subtract 18. Not a prayer. Negative 2? That's worth it. We probably ought to check it using synthetic division, because if you think about plugging in a negative 2, you're going to do a lot of calculations to see whether or not it works by plugging it in. If it does, you're going to have to do synthetic division anyway to produce the depressed polynomial. Got it? Okay, so let's check negative 2. We've got a 3, a 5, a 25, a 45, and a negative 18. Let's hope that it works. worked, didn't it? Okay, now, they do generally try and be nice. Occasionally, you might have to do synthetic division. You know, check 1 and 2, or check 1, -1. Maybe 2 or -2 don't work. Usually, by the time you get to the third or the fourth one, it's going to work. So, here's what we've got. I've got a 0 right here. That's a 0. That means I've got a factor of x plus 2. And then I've got a 3x. What does that start off with? Cubed minus an x squared plus a 27x and minus a 9. Now, were they nice on this problem?
Yes.
Somebody tell me why. Okay, this is a 4-term polynomial. Once you get to 4 terms or less, we've got some tools to deal with that, and hopefully this works. So out of here I can take an x squared. I'm left with a 3x minus a 1. Out of here I'm going to take a 9. I'm left with a 3x minus 1. So here's what I've got. I've got an x plus 2. I've got a 3x minus 1. And I've got an x squared plus 9. So this is where I sit right now. It would be nice if it were a -9. It's not. But if I take x squared plus 9, it's a quadratic. It doesn't factor with real numbers, but does that mean there aren't any solutions from it? Especially considering the fact we're talking about complex zeros. Move the 9 to the other side. Take the square root, and I get, lo and behold, plus or minus 3i. 3i and -3i, which are conjugates of each other. Okay? So that means I've got the x plus 2. I've got the 3x minus 1. Make that look like a minus 1. And I've got an x. Help me out here. I'm going to do the minus 3i and then x plus 3i. This is factored. Now, did it ask us to factor this? No, it didn't, but is it good practice? It is good practice. 0, -2. 1/3. 3i and -3i. There they are, and take a look. I've got 4 of them. 2 of them are nice. Are they on our list? Yes, they are. Okay? Any questions? Okay. All right. Have a great weekend. We'll correct 5-1 at the beginning of class. Sorry, 5-5. You should do enough of 5-6 that you walk into class on Monday and you know what you need to ask questions about. Monday is a Q&A day. I am going to give you a 1-problem quiz on 5.1 though. Other than that, it's Q&A, question and answer. Get the help you need. Get this figured out. John.
Where's